You wake up, but you don't have a body. No lungs, no heartbeat, no eyes. Just consciousness. You remember Earth, gravity, the smell of rain. You remember being born, growing up, reading this sentence. None of it is real. You are a Boltzmann brain, a random fluctuation of atoms in an empty universe. A ghost with false memories floating in eternal void. And according to some of our best theories about the universe, you are statistically more likely to be this lonely phantom than the person you think you are. The second law of thermodynamics is a one-way street. Entropy increases. Disorder grows. A shattered glass never spontaneously reassembles. Heat never flows from cold to hot. The universe is winding down. In the 1890s, this troubled physicists deeply. If entropy only increases, if disorder only grows, then why isn't the universe already maximally disordered? Why do we see structure, order, complexity? Why isn't everything just uniform chaos? Ludwig Boltzmann had an answer, one that would haunt cosmology for over a century. Boltzmann reframed entropy not as an absolute law, but as a statistical tendency. Imagine a box of gas at maximum entropy, uniform, featureless, dead. But wait long enough, truly long enough, and random thermal fluctuations will occasionally create pockets of lower entropy. By pure chance, particles might briefly cluster, form patterns, create temporary order. Ernst Zermelo, a mathematician, attacked this idea immediately. If entropy fluctuates, he argued, then the second law isn't really a law at all, just a statistical accident. Boltzmann offered two defenses. First, maybe the universe simply began in a low entropy state, for reasons unknown. This is now believed to be correct. The Big Bang was an extraordinarily improbable low entropy event. But Boltzmann offered a second, more speculative idea. Maybe the universe has always existed, eternally at maximum entropy, and our ordered cosmos is just a rare statistical fluctuation, a temporary pocket of order in an infinite sea of chaos. If that's true, Boltzmann realized, we can only exist in those rare fluctuations. We are, by definition, observers who find themselves in low entropy regions. This was one of the earliest uses of what we now call the anthropic principle. We observe a low entropy universe because only low entropy regions can support observers. It sounds reasonable. It's completely wrong. Here's the problem. To create our entire observable universe by random fluctuation requires an absurdly unlikely event. 10 to the power of 10 to the power of 123. Roger Penrose calculated this number. It's so large it doesn't fit in conventional notation. But to create just a single human brain, complete with neurons, memories, the illusion of having lived a full life, requires a vastly smaller fluctuation. Still impossibly unlikely, but infinitely more probable than an entire universe. In an eternal universe undergoing random fluctuations, for every one fluctuation large enough to create a cosmos like ours, there would be googles upon googles of fluctuations just large enough to create a single conscious brain. Which means, if Boltzmann's picture were correct, the overwhelming majority of conscious observers in the universe would not be humans who evolved over billions of years. They would be Boltzmann brains, momentary fluctuations, ghosts with false histories. including, statistically, you. Let's be precise about what we're describing. Imagine the far future. The universe has reached maximum entropy, what physicists call heat death. No stars, no galaxies, no structure of any kind. Just particles drifting in cold, dark equilibrium. But the Poincaré recurrence theorem tells us something strange. In a closed system with finite energy, given infinite time, every possible configuration will eventually recur. Which means, wait long enough, truly long enough, and those random particles will accidentally arrange themselves into any structure. A hydrogen atom, a molecule, a protein, a neuron, and eventually, by pure chance, a fully formed human brain. Not just any brain, a brain in exactly the state yours is in right now. Neurons firing in patterns that encode this very moment. Memories of your childhood, perfectly formed. The sensation of reading these words, complete with context. But none of those memories correspond to real events. They're just random information that happened to coalesce into coherent patterns. And almost immediately, within seconds, microseconds even, thermal fluctuations will dissolve it back into chaos. You would exist for one moment of conscious experience, and then, nothing. The mathematics is brutal. A fluctuation large enough to create our entire observable universe. With 13.8 billion years of history, 100 billion galaxies, countless stars, is exponentially less likely than a fluctuation that creates just our solar system, which is exponentially less likely than a fluctuation that creates just Earth, which is exponentially less likely than a fluctuation that creates just this room, with you in it, right now, which is exponentially less likely than a fluctuation that creates just a brain. No body, no room, no Earth, no solar system, just consciousness, floating in void, complete with false memories. This is the principle of minimal fluctuation. If consciousness can exist with or without a supporting universe, the version without the universe is immeasurably more likely. As cosmologist Sean Carroll puts it, if our theory predicts that most observers are Boltzmann brains, then either our theory is wrong, or we are Boltzmann brains. And if we're Boltzmann brains, then all our reasoning that led us to this conclusion is itself unreliable. We're trapped in what Carroll calls cognitive instability, a theory that, if true, gives us no reason to believe it's true. Ludwig Boltzmann never resolved this paradox. On September 5, 1906, while on vacation with his family, he hanged himself. He was 62 years old, depressed, embattled, brilliant. His equation for entropy is carved on his tombstone. S equals K times the logarithm of W. He never knew his ideas would be vindicated, that statistical mechanics would become foundational to physics, or that his thought experiment would return a century later to haunt modern cosmology. In 2002, cosmologists realized they had a problem. Observations showed that the universe's expansion is accelerating, driven by something called dark energy, or equivalently, a cosmological constant. If the cosmological constant is truly constant, the universe will expand forever, eventually reaching a state called de Sitter space, an eternally expanding, nearly empty void. And in that eternal future, thermal equilibrium returns. Empty space, maximum entropy. But crucially, not zero temperature. Even empty space has a temperature, the Gibbons-Hawking temperature, about 10 to the minus 30 Kelvin. Almost nothing, but not quite zero, which means quantum and thermal fluctuations continue forever. And if fluctuations continue forever, then Boltzmann brains aren't just a thought experiment. They're a prediction.
Between 2002 and 2008, physicists began publishing papers with titles like Disturbing Implications of a Cosmological Constant, Boltzmann Brains, and the Scale Factor Cutoff Measure. Andreas Albrecht and Lorenzo Sorbo made it explicit. If your cosmological model predicts eternal de Sitter space, and you calculate the ratio of normal observers to Boltzmann brains, Boltzmann brains outnumber real observers by factors so large they make Penrose's universe number look tiny. Physicist Brian Greene states, "I am confident that I am not a Boltzmann brain. However, we want our theories to similarly concur that we are not Boltzmann brains, but so far it has proved surprisingly difficult for them to do so." The Boltzmann brain problem became a test, a Reductio Ad Absurdum. Step 1. Propose a cosmological model. Step 2. Calculate the ratio of normal observers to Boltzmann brains. Step 3. If Boltzmann brains dominate, your theory is wrong. It's not that anyone believes Boltzmann brains actually exist. It's that any theory predicting they should exist is revealing a deeper flaw in our understanding. Sean Carroll calls this cognitive instability, a theory that undermines its own justification. If I calculate that I'm probably a Boltzmann brain, then my memories are probably false, which means my knowledge of physics is probably false, which means my calculation is probably false. The theory eats itself. But there's a deeper issue. Many modern cosmological theories involve infinite space-time, eternal inflation, the multiverse, endless cosmic expansion. In an infinite universe, there are infinite normal observers and infinite Boltzmann brains. So what's the ratio? Infinity divided by infinity. Undefined. To answer this, you need to choose a measure, a mathematical way of comparing infinite sets. But different measures give wildly different answers. Some make Boltzmann brains dominant. Some make them negligible. Some make the question meaningless. This is called the measure problem in cosmology, and it's unsolved. We don't know which measure, if any, correctly describes reality. Which means, even if your theory avoids Boltzmann brains under one measure, it might not under another. As cosmologist Leonard Susskind notes, we're not just uncertain about the universe, we're uncertain about how to be uncertain about the universe. So how do we escape? Solution 1. Maybe the universe isn't eternal. Maybe it has a finite past, a beginning. If the universe is only 13.8 billion years old, there hasn't been enough time for appreciable numbers of Boltzmann brains to form. But this only solves the past problem. If the future is infinite, Boltzmann brains still eventually dominate. Solution 2. Maybe our vacuum is unstable. Maybe the cosmological constant isn't truly constant. Maybe our universe will eventually decay into a lower energy state, destroying everything, including the possibility of future Boltzmann brains. Sean Carroll and colleagues calculated that if the Higgs field causes vacuum decay on timescales of tens of billions of years, Boltzmann brains never get a chance to form. This would solve the problem, but it requires very specific values for fundamental constants, values we haven't confirmed. Solution 3. Maybe quantum mechanics changes the game. In some interpretations of quantum mechanics, particularly many worlds, de Sitter space settles into a truly stationary vacuum state. No fluctuations, no dynamics, no Boltzmann brains. Carroll argues that observation requires dynamical evolution, out of equilibrium physical processes, neither of which exist in a static quantum vacuum. Therefore, no observers can form. Problem solved. Maybe. Not everyone is convinced. The debate continues. René Descartes tried to find certain knowledge. He doubted everything, questioned perception, memory, logic, and concluded, "I think, therefore I am. At minimum, my consciousness exists." The Boltzmann Brain Paradox suggests that even this isn't enough. You might be conscious, but if you're a random fluctuation, you have no reason to trust your thoughts. Existence without reliability, the loneliest philosophy. Let's confront what this really means. If you were a Boltzmann brain, every memory you have would be false. Your understanding of physics would be fabricated. The sun wouldn't exist. Gravity wouldn't be real. The Big Bang would be fiction. No one you've ever known would have existed. No history, no evolution, no Earth. Just you. For one flickering moment. In infinite darkness. Philosopher Michael Huemer argues that this casts doubt on the Big Bang itself. If our best theories make Boltzmann brains likely, and we're confident we're not Boltzmann brains, then maybe those theories, including the Big Bang, are wrong. Maybe the universe has no beginning. Eternally old. Eternally young. No need for an improbable low entropy start. But this just relocates the problem. An eternal universe still generates infinite future time, which means infinite opportunity for Boltzmann brains. The mathematics seems inescapable. So why don't cosmologists actually believe we're Boltzmann brains? Reason 1. Simplicity. We have two hypotheses. 1. You're a human, evolved over billions of years, in a universe that began with the Big Bang. 2. You're a momentary fluctuation with false memories. Both explain your current conscious experience identically, but one requires an entire consistent universe. The other requires only your consciousness plus fabricated context. Statistically, in a fluctuating eternal universe, the second is vastly more likely. But epistemologically, the first is vastly more reasonable. Reason 2. Our theories work. General relativity predicts gravitational waves. We detect them. Quantum mechanics predicts the Higgs boson. We find it. Cosmology predicts the cosmic microwave background. It's there. If we were Boltzmann brains with random false memories, the odds that those memories would cohere into a consistent, predictive scientific framework are essentially zero. The very fact that physics works is evidence we're not Boltzmann brains. But here's the catch. This argument assumes our reasoning is reliable, which is exactly what's in question if we're Boltzmann brains. We're arguing in a circle, but it's the only circle we have. The Boltzmann Brain Paradox teaches us something profound about doing science at the largest scales. In a lab, you test theories by controlling variables, repeating experiments, isolating causes. But in cosmology, your lab is the only universe you'll ever observe. You can't run the Big Bang twice. You can't test theories by comparing different universes. This forces us into anthropic reasoning. We observe what we observe because we must be in a region compatible with our existence. And suddenly, the boundary between physics and philosophy dissolves. What does it mean for a cosmological theory to make predictions if we can only observe one outcome? What role does consciousness play in determining which theories are viable? How do we define probability when dealing with unique, unrepeatable events? These questions keep cosmologists awake at night, not because they lack intelligence, but because they're genuinely difficult. Perhaps the most difficult questions humans have ever asked.
So are you a Boltzmann brain?
Probably not. Almost certainly not. But the fact that we have to say probably tells you something. We live in a universe we're still trying to understand. Our best theories predict things that can't be true. Our observations constrain theories we haven't imagined yet. And sometimes, the most valuable use of a thought experiment isn't to describe reality, but to show us where our thinking breaks down. The Boltzmann brain isn't a prediction. It's a warning sign. When your theory predicts that most observers should be ghosts in a vacuum, you don't conclude you're a ghost. You conclude your theory needs work. Maybe the universe has a finite past. Maybe vacuum decay will save us. Maybe quantum mechanics changes the rules. Or maybe we're missing something fundamental about entropy, time, or consciousness itself. Ludwig Boltzmann never lived to see his statistical mechanics vindicated. Never knew that entropy would become central to understanding the universe. Never imagined that his thought experiment would return a century later to challenge our deepest cosmological theories. But his legacy endures, carved in stone, woven into the fabric of modern physics. We haven't solved the Boltzmann brain problem. We may never solve it completely. But in trying to solve it, we're learning something more important. The universe is under no obligation to make sense to us. Our intuitions evolved to hunt gazelles and find shelter, not to comprehend eternity, infinity, or the statistical mechanics of consciousness. The fact that we can even formulate questions this deep is remarkable. The fact that we don't yet have answers is humbling. This is Cosmic Canvas, where we confront the universe's deepest mysteries, even when those mysteries confront us back. Until next time, trust your memories, question your theories, and remember, you're probably real.